In order to understand the concept of electric potential energy, I'd like to go back really quickly and discuss or rehash gravitational potential energy just to make sure we can see some of the connections. So, we're going to take a look at this classroom, and we'll assume this is a gravitational field within the classroom. The lines will show the direction of force that will act on any mass placed in this gravitational field. So, this would be the roof or the ceiling of the classroom, this would be the floor. If I placed any kind of mass into this gravitational field, the force that acts on it would be downward. We can also hopefully remember that if I choose a reference point, which for most cases will be the ground, so if our reference point is the ground of the classroom, you'll notice that any height above this reference point, you're going to get some type of gravitational potential energy, which we denote with capital E lowercase g. So if we remember back, the gravitational potential energy that an object has will be its mass times the gravitational field that it's placed in, or the acceleration due to that field, which on Earth is 9.81, times whatever the height above our reference point is. So that's how we calculate our gravitational potential energy. If I'd like to increase my gravitational potential energy, I will increase my height or my mass. If I'd like it to decrease, I will decrease my height or decrease my mass. With gravitational fields, we can't really change them, so these are the only two options that we're going to really look at. Now, in terms of electric potential energy, it's actually very, very similar. The difference is instead of a gravitational field, we're talking about an electric field. So I've drawn two parallel plates, they have equal charge, and I've drawn the electric field represented by these downward arrows. If you remember, electric field lines point away from a positive towards a negative, and that has to do with the fact that they represent the force that would act on a positive test charge at any location. Now, the main difference between electric potential energy and gravitational potential energy is that gravitational potential energy is based on a mass located in a gravitational field. And electric potential energy has to do with charge being placed, in an electric field. So we denote it as E for energy with sub E for electric, so electric potential energy. We just have to think back. While gravitational is mass placed in a gravitational field times the height above a reference point, electric potential energy is pretty much the same thing. If I choose my reference point not being the ground, but if I instead choose this bottom plate to be my reference point, well, this charge, wherever I place it, will be a certain distance above my reference point. Now, the reason I use distance instead of height is because, for an example like this, it would make sense to do height, but sometimes these fields are drawn sideways or they're drawn upside down. It all depends on how you're given the problem. So it's a little bit better to say distance because then you're not kind of stuck and tied into this one example where everything acts down. So the difference being we're not dealing with mass, we're dealing with charge. We're not dealing with a gravitational field, we're dealing with an electric field. And instead of height, kind of the same concept, but we're talking about distance. So instead of mgh, we're just dealing with QED. Same basic concept. Charge instead of mass, electric field instead of gravitational field, and distance, essentially height, just depends on the orientation of your example. So, ways I can increase the electric potential energy, well, I could increase the charge, I could increase the distance from my reference point. This is a unique example in the sense that based on the amount of charge we put on these plates, we can actually also control the electric field strength. So we can actually change any one of these. We could also do the same for gravitational potential, but we don't really have the technology right now, so to say, in order to actually change the gravitational field. At least when we're talking about Earth, that's the case. So just understand right now the connections between these two. Same basic concept. Instead of like the roof and the ground, we're talking about a positive and negative plate, charges instead of masses. Now that leads to the next big question, and everyone always wants to know, does that charge gain or lose whatever energy that we're considering? If I calculate the amount of energy using this equation, if I know the charge, I know the electric field, and I know the distance it's been moved, I should be able to calculate its electric potential energy. Just like if I know the mass, the gravitational acceleration, and the height or the distance that that object has been moved, I should be able to calculate the gravitational potential. Now, in order to understand or to determine whether it gains or loses the energy, there is one major question. This should be in your notes. You should have about 5,000 stars next to it. And that major question is the charge, so whatever charge you're talking about, whatever charge is being moved within the problem, is the charge doing what it naturally wants to do? And I say wants to do, obviously it doesn't want to do anything. But if you have a negative charge, that negative charge is going to want to move towards a positive charge. So a good way to look at it, if I use the same example that I kind of had on the previous page, if I have a positive plate up top and I have a negative plate on the bottom, hopefully you see that the field will be directed in this direction. Well, if I take a positive charge and I allow it to move this certain distance, well, I have an electric field, I have whatever that charge would be, and I have the distance that it moved. So I should be able to calculate my electric potential energy. But is it gaining or losing this energy? That's what tends to be tricky. And all you have to think is the charge doing what it naturally wants to do. Well, this is a positive charge, and it wants to be near a negative charge. I'm allowing this to do what it would like to do. Just like in a gravitational field, if I let a mass drop towards the ground, that's what it naturally wants to do. So if we think about it, a mass that drops down towards the ground or does what it would like to do, that loses gravitational potential energy. So if the answer to this question is yes, it is doing what it wants to do, then you have a net loss of energy. It's actually losing energy. All right, we think about a mass in a gravitational field. If I were to take that mass and I were to raise that up towards the ceiling, well, it's not actually doing what it naturally wants to do. Just like if I took this positive charge and I moved it in the other direction, that's bringing it closer to a positive plate. That is not what it naturally wants to do. So it's gaining energy. Okay, so much like raising a mass towards the ceiling where it doesn't necessarily want to naturally be will give it an increase in gravitational potential energy. Taking a positive charge and moving it towards a positive plate will also result in a gain of energy because it's not doing what it naturally wants to do. This is a very important question. It's going to be the easiest way to kind of understand what's going on in these situations. So just to show you guys a quick example, I have 4 situations here. I'm going to give you guys a little bit of time to kind of figure out what's going on here. But what I'd like to know is, in this situation, if I have a positive charge and I allow it to move this way, or I have a negative charge and I allow it to move this way, I want to know whether or not I'm gaining or losing energy. Likewise, I will place a positive here and a negative here. And these are just showing you the sign of the charge and the direction that I'm moving them within the field. So if I take a few of these, that'll be negative. And what I'm going to do is I'm going to take a look, and I want you guys to try and figure out what's going on here. Are the positive charges gaining or losing energy? Are the negative charges gaining or losing energy? So we take a look at this example here. I have a positive charge. I'm allowing it to move towards a negative plate. So if you think about this, the positive would naturally like to go towards the negative. So in this case here, I have a loss of energy. The charge is naturally doing what it wants to do. It's losing energy. If I take a look at this case, I have a negative charge being forced, in this case, or being moved towards a negatively charged plate. That is not what it naturally wants to do. I'm therefore gaining electric potential energy. If I look at this case, this negative charge does not want to naturally go near this negative plate. So this will be an example of a gain of energy. This positive, likewise, does not want to be near this positive. So this is also a gain of electric potential energy. This positive charge down here would like to naturally be near this negative plate, so this is a loss. Just like that mass dropping towards the floor is losing gravitational potential energy, this positive charge naturally wants to go towards the negative, it's losing energy. This negative does not want to be near this negative plate, so that would be a gain in electric potential energy. Hopefully you're starting to see how we figure out whether or not this energy is gained or lost. You can hopefully see that this one will gain energy. It is doing the opposite of what it would like to do. And likewise, this negative charge is also gaining electric potential energy. It does not want to be near this negatively charged plate. Hopefully you guys are seeing a little bit about how to determine whether or not energy is lost or gained, and maybe a little bit about why it's actually gaining or losing this energy. I have two other quick examples I'd like to go through just so you guys have a better idea of what we're talking about here. And what you're given an electric field. You're being told that it is 215 newtons per coulomb. You can see this is a uniform field, so that will be the same throughout. And a proton is being moved from point A to point B. So a proton is being moved 2 centimeters through this electric field. Think about it as if it were a mass. A mass is being moved through an electric field. So just like that mass would gain, I apologize, just like a mass moving through a gravitational field would gain or lose energy, a charge moving through an electric field will likewise either gain or lose electric potential energy. So we're given a few things here. We're given that the electric field is 215 newtons per coulomb. We're given a proton, and the proton is or has a charge of 1.6 times 10 to the negative 19 coulombs. And they're asking us, what is that change in energy? So what is that electric potential energy? And we're also given that there's a distance of 2 centimeters, which is 0.02 meters. So if we list everything we're given the charge, the electric field strength, and the distance through the field that it is moved, and we're asked to find the electric potential energy. Well, if we think back to our original equation, we know that instead of a mass times a gravitational field times the height that it's moved, it's charge times the electric field times the distance that it's moved. So all I have to do here is 1.6 times 10 to the negative 19th times 215 times the 2 centimeters or the 0.02 meters that is moved through the field. If I plug that in my calculator, we should get 1.6 times 10 to the negative 19th times 215 times the 2 centimeters, and I wind up getting somewhere around 6.88 times 10 to the negative 6 joules. That's the amount of energy that it either gained or lost. Now, in order to determine whether it gained or lost, well, I'm talking about a proton, which is a positive charge. So if I placed a proton at A and I moved it towards B, a positive is going towards the negative. That is what it naturally wants to do. So this would be a loss of electric potential energy. So that's the type of example you would be expected to solve. I've included this one just to show you that the electric field will not always necessarily be up and down. It could be left to right or right to left. It could be from the south to the north. It could be any one of these examples. So here we're given a similar problem, point A and point B, separated by a distance of 5 centimeters, and the electric field strength is given as 200 newtons per coulomb. We're asked, a charge is moved from point A to point B, so the charge is moving in this direction. The electric field is 200 newtons per coulomb. As a result of that movement, if it gains 4 times 10 to the negative 6 joules, I'm going to underline that will become important, gains that much energy, what is the unknown charge? Well, we know that the electric potential energy is a charge that is moved through an electric field. We don't know the charge, so the charge is unknown. We know the electric field strength is 200 newtons per coulomb, and we know that it's moved 5 centimeters, which would be 0.05 meters. We also know that it gains 4 times 10 to the negative 6 joules of energy. So if we go through and we solve for Q, we should take 4 times 10 to the negative 6th. We can divide that by 200 and divide that by 0.05. What we wind up getting is 4 times 10 to the negative 7th coulombs, but we need a sign on that. Well, we have to realize if it's gaining energy by moving from A to B, gaining means it does not, or it is not doing what it currently wants to do or naturally wants to do. So what type of charge could I move from A to B that would be gaining energy, meaning you're making it do what it doesn't want to do? Well, it's getting closer to a negative plate. If it's not what it wants to do, the only charge that would do that would be a negative charge. So negative 4 times 10 to the negative 7th coulombs, that is the only charge that you can move from A to B, have this much energy, and have that much energy gained because you're making it do what it naturally does not want to do.